Hi, welcome to a problem session, the problem session for lecture 16. This is going to cover a little bit of comparative statics and stuff on implicit differentiation, and is the last problem session of this part of the course and the course as well. So, let's begin by discussing briefly comparative statics, what they are. If you go through and solve a problem with to find an optimum, say behavior, or any other optimum you want from a function, sometimes you can explicitly define your optimum in this fashion with some parameter c, and it might look like this. This happens when you can go through and solve your first order condition and actually get an equation that you then solve for the optimum x star, and it might be a function of some parameters. Now when you have this kind of thing, if you want to go about and actually figure out how this thing changes with the parameters, you just take the derivative of this thing with respect to the parameter, and this is a total derivative, not a partial derivative here. Well, here it's just 3 minus 2c, and that's it. There's nothing fancy to do here. We take a single first derivative, and we can say that it's less than 0 if c is less than 3/2, and it's greater than 0 if c is greater than 3/2, which tells us the sign of the comparative static here, which is usually what is of interest to us, is the sign, whether or not we think that the optimum is increasing or decreasing in the parameter. This is what we discussed in the lecture itself. Okay. So that's what happens if you have an explicitly defined optimum. Oftentimes, though, you can't actually solve for your optimum explicitly, and you're forced to actually look at the implicit definition of the optimum. When you do this, when you have an optimum defined implicitly, then you can either use the implicit function theorem or total differentiation to get at the way in which the optimum changes with the parameter. So for example, assume that the party's utility for policy depends on the extremity of its policy position. It has some not realistic, admittedly, form that looks like this. Now, this thing's utility function is not what defines the optimum. Right? What defines the optimum is the first order condition, which is a derivative of the utility function. So here, z is a parameter in this case, so we can ignore it. We just pull down the z out front, negative z out front of here, in the first term, and the second term is going to be that. Now, typically what we do is we take the first order condition, we set it equal to 0, but to give us the first order condition, rather, we take the derivative equal to 0 to give us the first order condition, and the x star that satisfies this equation is your optimum x star. Now, it'd be great if you could actually go about and solve for x star here, but you can't. You have an x star on one side and an e to the x star on the other side. That's a transcendental equation you can't find the closed form solution for. So, what we do instead is make this whole equation equal to f, and use the implicit function theorem to find dx star dz. What is that? Well, we need a couple of partial derivatives to do this. The first partial derivative we need is df partial f partial z. Well, going back to your function right here, that is a product root situation. The first term is over here is negative e to the negative x star minus z times z. That's the first term. The second term has minus z. Now here the actual exponent is negative xz negative xz plus z squared. So you're going to pull down 2z. So you're going to pull down a 2z from this minus an x star, and then you're going to get this back again. Right. And then there's another term which I should have left more room for, which is the plus, oh, I have room for that, plus 2 at the end there. Okay. And that gives us that derivative, and this derivative is a partial derivative back to x. This is a little simpler. Again, we just pull down in the first term another z, so we get z squared out front. Sorry, a negative z, so it's positive now. And we get a minus 2 over here. Why do we do those two things? Well, because this derivative over here, by the implicit function theorem, is partial f partial z divided by negative that, partial f partial x. So this whole derivative, which is what we want in this case, that should be a z in the first place, equals this over the first over the second, or negative e to the negative x star minus z times z minus z to z minus x star e to the negative x star minus z. I really should combine those two things, plus a 2 divided by z squared e to the negative x minus z times z minus 2. And there you go. That is your complete derivative. And if you happen to know that x star are positive, and potentially the size of these things, you might be able to figure out a sign for this. Oftentimes you can't figure out a sign for these things, but this is the only way you can actually go about trying to see if you can figure out a sign for this stuff. Okay, so there you go. So that's a case of the implicit function theorem in one dimension with one parameter. Here's the relevant function equation you need. It's a very useful equation, and again, as we did in the lecture and the book, you can go through and derive that equation pretty easily by using total differentiation on the first order condition. Okay, so there you go there. Now I'm going to do one more example, though, that's more complicated. And this is actually from the book. In the book, we have one in which we have a general functional form pi for a particular scenario. And then in the problem set for the book, and the exercises at the end of the chapter, rather, go through and solve that one for a particular functional form. There, the solution set illustrates what the answer is, but I think it's pretty helpful to go through and use this as a sort of go through a little slower than the work solution does, and talk through exactly how this works in the process you do this and what it means, because it can be fairly complicated to use the implicit function theorem in more than one dimension. There is a simpler example that is really helpful to go through and do all the math for yourself as the last problem in the problem set for this lecture. Okay, but we're going to go through the book's version of this. So in the book, it proposed that the chance of something happening, it doesn't really matter what at this point, is that. And now we have functions that look like this. First order condition. So the two actual functions look like pi. So the first one is pi minus. So person of 1's utility is pi minus 1/2 c1 b1 squared, and 2's is going to be 1 minus pi minus 1/2 c2 b2 squared. And then you need the first order conditions now. Now, an interesting fact about the derivative of pi, I think it's interesting, is that if you take this, what's that? Well, this thing is equal to 1 plus e to the b2 minus b1, all to the negative 1 power, because 1 over that is just to the negative 1 power. So the derivative is going to be this to the negative 2 power times the derivative of the thing inside here, using the chain rule here. Well, what's that? That's going to be, and I pulled the negative 1 for this. Well, it's going to be negative e to the b2 minus b1. So this thing is going to be, negatives cancel. I get e to the b2 over b minus b1 times 1 plus e to the b2 minus b1. And I'm going to write it this way to show you how this works. Times another one. So I'm basically going to take a square and split it apart into two different terms. Why did I do that? Well, because this thing is 1 minus pi, and this thing is pi. So it turns out the derivative of an exponential like this is going to equal pi times 1 minus pi. There's a minor difference if you do with respect to b2, because b2 does not have a negative out front of it in the exponent. There's no negative over here, so with respect to b2, this is negative pi 1 minus pi. Otherwise, it's the same. Okay, so that can be kind of helpful very shortly. Now, in more than one dimensions, you saw in the lecture, we need to calculate two different Jacobians. So we're going to calculate two ones. The more complicated one is the one with respect to the action vector b rather. This thing looks like this. Now there's two functions we have here, f1 and f2. Oh, which I didn't actually write down yet. I apologize. So this implies f1 is the derivative of this thing using the stuff we just did, is pi times 1 minus pi minus c1 b1. And this thing implies it's there's a negative out front already, though, so the negatives cancel with negative over here, and you get the same exact pi times 1 minus pi minus C2B2. So there are two F1s and F2s. Let's equal to F2. Okay, so the Jacobian, back to the Jacobian again. So we have to take derivatives of F1 and F2 up here with respect to the different variables again. First row does the derivatives of F1. So the first row, first element is the derivative of F1 with respect to B1. Now, what's the derivative of pi times 1 minus pi? We'll use the chain rule. That's pi times 1 minus pi is actually pi minus pi squared. So that's 1 minus 2 pi times the derivative of pi. The derivative of pi is pi times 1 minus pi. So we get up here pi times 1 minus pi times 1 minus 2 pi. Again, if that was too fast, which it quite possibly was, and also written kind of small because I have a lot of stuff to fit in this one screen, stop, make sure you can go through and do this carefully and see if you're comfortable with it. Okay, so that was that. So that's the first term. The second term, there's a B1 in there, so that gives you minus C1. Okay. The second element is the derivative of U1 with respect to B2. That's again pi times 1 minus pi times 1 minus 2 pi, except now there's a negative out front because the derivative with respect to B2. Okay. Next one. The second row of the Jacobian has the derivative of F2 with respect to B1. That is, again, pi times 1 minus pi times 1 minus 2 pi. And finally, the last element of the Jacobian is the derivative of F2, the partial derivative, with respect to B2. That gives us a negative pi times 1 minus pi times 1 minus 2 pi, and then also a minus C2. And there you go. So that's the Jacobian, the harder Jacobian to calculate. And that's also the one we have to actually take the inverse of. We can find the determinant. It's top left times bottom right minus top right times bottom left. It looks really messy at first, but it simplifies a bunch, so I'm just going to write down the answer now. You should go through and make sure you can actually do that yourself. The determinant, because I have very little room here, the determinant of the Jacobian is going to be C1 minus C2 times pi times 1 minus pi times 1 minus 2 pi and plus C1, C2. Okay. So, the inverse of the Jacobian then, and I'm probably going to have to violate my rule about not doing this, is 1 over the determinant of the Jacobian, we just wrote, times, we flip these two to get negative pi, 1 minus pi, 1 minus 2 pi, minus C2, and change the signs in the off diagonals, get pi, 1 minus pi, 2 pi, change the sign over here too, and finally put the one for the upper left and the lower right to get minus C1 group. Okay, there you go. We need one more Jacobian for C. This one's much simpler. There's only one C in F1 and only one C in F2, so it's going to be a diagonal matrix. Looks like this. Now we must multiply negative JB inverse times JC to get the overall answer. And I apologize, I have to go on a different page, different screen now because I can't write this and make it at all legible. And it's important for it to be legible to understand it. So stop here for a second, make sure you get everything on the screen. I'm going to copy over, I'm just going to multiply JB inverse times JC, which involves taking the first row times the first column, dotting with that. That's the upper left element, and so on. I'll do the whole thing out. Stop here for a second, make sure you can do it out yourself. Maybe do it first, and then check in the next second when you go forward again. I'm going to move on now. When you multiply the two things together, you get this large thing, which I'm going to write all out because it's helpful. which is 1 over the determinant, which was written out a little larger. Times a large matrix. Actually, I'm just going to make a whole different thing here. That's a times, because it's going to be large, and I don't want to write too small so you can't read it. Okay, and there you go. So that is the Jacobian. Now, one of the reasons I want to do this for the last example here is it's not obvious what this means all the time. So I'm going to elaborate on what we did in the book and in the lecture to be clear exactly what this means. Now, the first column here represents the change in both persons. The first column represents the change in with respect to C1, and the second column represents the change with respect to C2, right? So this helps us understand exactly what's going on here. So the first row represents the change in B1 with respect to each of the two variables, and the second one tells us the change in B2 with respect to each of the two variables. So let's look at the first row. The first row says that you have a negative, so this first term here depends on whether or not 2 pi is greater than or equal to 1, the sign of that. And that's true for every single one of these. Similarly, that same thing appears out front in the Jacobian, in the determinant, and also there's a second thing that matters. There's a C1 minus C2 out front. So the sign is not obvious, but we can make some particular examples. So let's say C1 is greater than or equal to C2, and pi 1 is less than 1/2. Actually, let's just make this just greater than. Right? So this is one particular case. If C1 is greater than C2 and pi is less than 1/2, then 1 minus 2 pi is positive, and C1 minus C2 is positive, which makes the determinant positive. It also makes all these individual terms in here positive, so all that matters is the sign out front of them. That means this is negative in that case, this is positive, this is negative, and this is positive. That tells us that B1 in equilibrium, B1 star, is decreasing in C1 and increasing in C2. The second row tells us that B2 star is decreasing in C1 but increasing in C2. Note, we're actually saying explicitly that the size of B2 star is increasing in the cost of doing B2 of actually doing B, of actually choosing higher B's. That kind of thing can only be true when you have these linked utilities, because what's happening is the indirect effect of increasing C2 on B's action is counteracting the direct effect of increasing C2 on 2's action, right? So again, the indirect effect of increasing C2 on 2's actions via how C2 changes B1 is providing sufficient counterbalance, is counteracting the direct negative effect of increasing C2 on 2's action, on 2's desire to produce B2, right? So there's this indirect effect in that C2 changes, that leads player 1 to alter its choice, and that altered choice provides an additional incentive to player 2 to alter player 2's choice. That incentive can be countered to the incentive provided by the increased cost. But if the indirect effect swamps the direct effect, you can actually get an increase in action in activity with higher cost. Right? And this kind of thing, again, is only possible when you have these joint linked utility functions, these jointly linked functions that define your optima across two different dimensions here, two different people. So that's why we end up using this, even though this is this is more complicated than the one-dimensional case. It's important because it helps us understand how these linked strategic decisions are affected by a change in a single parameter in a way you can't do by just taking a single partial derivative of a single equation, because then you miss these indirect effects. And you can go through if you want and look at other possible cases, right? If C1 is less than C2, but pi is less than 1/2, then everything we said is opposite, and both actions are increasing in because the determinant's the negative, and both actions are increasing in C1 and decreasing in C2, and so on with the other options with pi greater than 1/2. That's it. That's how you use this stuff, and that's the end of this problem session, the end of all of our problem sessions. I thank you very much for listening.